Good afternoon, Causeway. The end of everything. As you can see from the subtitle, I'm talking about the fate of the Earth, the Sun, the galaxy, and ultimately the fate of the universe. So we're going to eternity and beyond, if you'll forgive me paraphrasing Buzz. I'll be giving a short prologue and then looking at the future of the Earth, the Sun, and the solar system. And then looking further to the future, asking what's going to happen to all the stars in the galaxy and indeed all of the other galaxies. And ultimately, the far, 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 far future and the ultimate fate of the universe. And then, so as not to leave you all thoroughly depressed, I'll finish with a slightly more upbeat epilogue. So yes, a few months ago, I gave you the beginning of everything, in which I described how we think the universe came to be 13.8 billion years ago and expanded until it was about the size of a golf ball, by which I mean the observable universe, which is currently 100 billion light years in diameter. All of those objects within the observable universe used to be a lot closer together, only a few centimeters apart. But since then, the universe has expanded until it's the size we see today. But this afternoon, we're looking at where we go from here, from the 13.8 billion year point to the future. So to try and keep track of where we are, I've got this timeline running along the top. Each box there represents 10 times further into the future than the previous box. So we'll be looking, for instance, maybe 1,000 years into the future, 10 to the 3, 10 to the 6, a million years, 7, 8, 9, a billion years into the future, 11, 12 trillion years into the future. So that's the way we're going to try and keep track. A red rectangle will move across from left to right as we go further and further and further into the future. And I'm indebted to the work of Adams and Laughlin, who published a paper some 25 or more years ago, in which they laid out the timescales on which many astrophysical phenomena are likely to occur, and I've used their paper to try and get all my slides in the right order. So one thing that we know is going to happen in a few thousand years, I'm not going to dwell on the next 10 or 100 or whatever years. Let's assume we get climate change under control. Let's assume we don't have a nuclear war. We know that on a timescale of 10 to the 4 years into the future, the pole star is going to change. Because of the precession of the Earth's axis points to a point on the sky which is tracing out a large circle. So at the moment, on the right-hand side there, the North Star is Polaris. But in another 10,000 years, because this cycle is 26,000 years, on a timescale of order 10 to 12,000 years, the pole star is going to change and it'll be Vega, making it a lot easier for Boy Scouts to point out which way is north. But there's another consequence for the pole star changing, and that is at the moment, because we are nearer to the sun during northern winter, because our axis points towards Polaris, it tends to mitigate to some extent the severity of the seasons. But when the pole points towards Vega, we're going to be nearer the sun at perihelion during northern summer, and that's going to exacerbate the seasons somewhat. And these collectively, these variations in the Earth's climate that are due to changes in the Earth's spin or changes in the Earth's orbit around the sun, collectively these are called Milankovitch cycles, and we'll see that again shortly. On a timescale of 10 to the 5 years into the future, we know that Voyagers are going to pass through other solar systems. Voyagers launched in the 1970s, passing the outer planets, Jupiter, Saturn, Uranus and Neptune. We know that these Voyagers are now heading out, and we can work out which way they're going and calculate which star systems they are likely to pass through. So for instance, at the top of the diagram, Voyager 1 is heading off towards the star system Gliese 445. At the bottom of the diagram, Voyager 2 is heading off in a different direction and will pass through the system Ross 248 on a timescale of many tens of thousands of years. Pioneers were launched a bit earlier, but they're travelling more slowly. Pioneer 10 on the right there is heading off in the direction of Aldebaran, and Pioneer 11 on the left is heading off in the direction of the centre of the galaxy. We know that we are in for ice ages on a similar timescale of order 100,000 years or so. Historical records tell us that we've had ice ages on this sort of time scale. The Earth entered an interglacial, a so-called warm period in between ice ages, relatively recently, and therefore we can say that we're due for an ice age on a timescale of order 10 to the 5 years into the future. This is another manifestation of a Milankovitch cycle due to changes in the Earth's orbit. Still on a timescale of 10 to the 5, 100 years into the future, we know that the Earth is slowing down and will continue to do so for thousands of years to come because of the tidal effects of the Moon. Basically, the Moon is stealing some of the Earth's angular momentum. At the moment, that means we add leap seconds every once in a while. We haven't done for a few years, but for the last few decades, we've been adding a leap second every once in a while to keep the Earth's rotation synchronized with our clocks. In other words, to keep our clocks synchronized with the Earth's rotation. But at this particular point in the future, 100,000 years into the future, the slowdown of the Earth would mean that we wouldn't be simply adding a leap second once every few years. We would have to add a leap second every day. In other words, the Earth would have slowed down by this point, we calculate. Instead of a rotation period of 24 hours, it would be 24 hours and a second. We know that some stars are going to go supernova. We can't predict exactly when, but we think on a timescale of 10 to the 5 years, we can expect Eta Carinae, a very massive star in the southern hemisphere, to probably go supernova. For the last few thousand years, it's been sloughing off some of its outer layers, producing this nebula that is currently surrounding the star. This is a sign that the star is getting very unstable, and we know it's at the right sort of mass to be a supernova candidate. It might be beaten to the punch by Betelgeuse in the northern hemisphere. Here's an astrophotographer who's taken a view of the night sky and then artificially brightened Betelgeuse, as you can see there in the constellation of Orion, to give an indication of what it might look like when it goes supernova. It'll probably be bright enough not only to be spectacular during the night, it'll probably be visible during the day as well. But supernova aren't the only possible stars that can explode in our vicinity. Betelgeuse is some 600 light years away and is not necessarily a threat to us. But there are some stars when they die that might conceivably be a threat. Wolf-Rayet 104, for instance, is 7,000 light years away, which might sound safe because it's considerably further away than Betelgeuse. But its death may result in a radiation burst even more powerful than a supernova. Wolf-Rayet stars are relatively massive and they have rapid rotation systems which produce jets. And if, when they die, a huge amount of radiation comes out on these jets, if the jet happens to be pointing in the direction of Earth, then that could be a problem, even at this enormous distance. We don't think these jets are pointing directly at Earth for this particular Wolf-Rayet star, but it's something we've got to keep an eye on. On a timescale of 1 million years into the future, all of the stars that we see in the Milky Way are orbiting around the centre of the Milky Way, effectively on independent orbits. And the Gaia spacecraft has been looking at all of these stars in our neighbourhood for quite a few years now to see how they are moving. And because we are all moving independently around the centre of the galaxy, every once in a while we just happen to come close to other stars. And it's been calculated that Gliese 710 is a star that will happen to come close to us on this timescale. It'll actually come close enough to actually enter our Oort cloud. So that means its gravitational pull is going to disrupt the orbit of a lot of these tiny, or not necessarily tiny, but relatively small icy bodies in the Oort cloud, and it will mean that some of these will come raining down into the inner solar system and probably result in naked eye comets, perhaps once every few weeks for 1 million years because of this gravitational disruption. So you can see it's going to come close and then disappear again. Not disappear, it's going to then move away from our sun again. But for a while, our solar system will have 2 suns, just like other planets we can think about. Still on a timescale of 1 million years into the future. Am I showing a picture of meteor crater because we can expect an impact like this every million years? Well, no, this was actually only a few tens of thousands of years old. We can note whilst we're here, wasn't it lucky that this impact just missed the visitors centre by that much? What a stroke of luck. No, the reason I'm showing this with a timescale of 10 to the 6 years is that any craters similar to this that were made more than 1 million years ago are going to be eroded because of the weathering systems on Earth. So we might not be aware of any impacts more than 1 million years old. You might say, yes, that weathering systems, we can understand how they work on Earth, but they don't operate where you haven't got an atmosphere. Well, it's true that the moon hasn't got an atmosphere, but it is being pulverized with micrometeorites all the time. So even the Apollo footprints on the moon are not going to last beyond this sort of timescale, because the pulverizing effect of these micrometeorites will effectively remove any trace of footprints. And if you were to wait long enough, these micrometeorites would effectively erase all evidence of the Apollo landings completely. 10 to the 7 years into the future, 10 million years. The Pioneer 10 and 11 spacecraft are flying out of the solar system, and they contain plaques which give an indication of where the spacecraft has come from. There's a pulsar map on the left-hand side, and a little cartoon at the bottom says this spacecraft came from the third rock from the sun. But on a timescale of 10 to the 7 years, the plaque, both the plaques on Pioneer 10 and 11, are going to become pitted and eroded and become unreadable. And that's simply because interstellar space is not empty, it's full of tiny grains of dust, and as the spacecraft fly for millions of years, the dust specks pummeling the plaque will eventually make the plaque unreadable. So pioneers will be going through hundreds, if not thousands, of solar systems on this timescale. If they get picked up by an alien civilization on a timescale less than 10 to the 7 years, they'll be able to read the plaque and tell where the spacecraft came from. But if it doesn't get picked up until it goes through a solar system after about 10 million years into the future, then it's unlikely that the civilization will be able to work out where the spacecraft came from. On a timescale of 10 to the 8 years into the future, 100 million years into the future, we can ask what's going to happen to something like Saturn's rings, for instance. But before we ask what's going to happen, we might ask ourselves, where did they come from in the first place? So did the moon Mimas, for instance, or a moon similar to Mimas, get pulverized and end up producing all of the debris, which ultimately resulted in Saturn's rings? You look at a moon like this and you might think to yourself,
that's no moon, it's a space station.
Because indeed Mimas does bear a striking resemblance to the Death Star from Star Wars. But simulations have been carried out by starting with a mass approximately equal to the mass of Mimas, and saying if you start with a planet like Saturn and take a small moon and pulverize it, let's assume that it gets hit by another moon, or maybe a comet comes into the solar system and smashes into the moon and pulverizes it. What happens to the cloud of debris that would result? You might assume that that cloud of debris would simply continue orbiting around Saturn for quite a while, but simulations have indicated that it doesn't take long for a ring system to develop. Look at the timescale in the bottom right. It only takes days or weeks for a ring system to form because of the continual interactions of all the tiny particles in the debris cloud that was produced. It doesn't take long for them to spread out into the entire orbit and generate a ring system. And again, because of the interactions of all the tiny particles, they will slowly spiral in towards Saturn. Over millions of years, that ring system has developed into the ring system we see today, partly shepherded by a whole load of moons as well. But that process is ongoing, and it's been calculated that on a timescale of 10 to the 8 years into the future, the inward spiral of all of the particles in Saturn's rings would ultimately mean that the ring system would effectively disappear and all of the ring particles will rain down onto the surface of Saturn. So for those of you who enjoy the view of Saturn and its rings, Make sure you make the most of it now, because they won't be there in a few 100 million years. Still on a timescale of 100 million years, we should remind ourselves that not only do things like Saturn's rings change on this timescale, but the solar system itself, which we tend to think of as clockwork by building ourselves orreries or tellurians to indicate how the Earth, Moon, Sun, or how the various planets move around the Sun, we should remind ourselves that actually the solar system is a chaotic system. Yes, it's possible to calculate where the planets were thousands of years ago, and it's possible to calculate where they will be thousands of years into the future with amazing accuracy. But we can't go an indefinite period backwards or forwards. We think the solar system was very different in the very early stages of its formation, and we don't even know what it's going to look like in a billion years' time. It could be that Jupiter has decided to eject one of the smaller planets, or maybe some of the planets would rearrange their orbits. It's effectively impossible to predict on timescales beyond, let's say, 100 million years or so. Still on a timescale of 10 to the 8 years into the future. At the moment, the Sun is sitting there in between a couple of spiral arms of the Milky Way galaxy. And because the Milky Way rotates on these sorts of timescales, on timescales of order 100 million years or so, it's been calculated that although at the moment we are sitting in between two spiral arms in a relatively sparsely populated part of the Milky Way, on this timescale we'll move from a low density region into a spiral arm, in other words, a higher density region. And then we will have rather more stellar neighbours than we have at the moment. So at the moment, for instance, there aren't many stars within 10 light years of us. But it's been calculated that when we move into a spiral arm, we will have considerably more neighbours that are quite close. And there are at least two consequences of having a lot of stellar neighbours. One of them we've sort of already mentioned. When Gliese 710 comes close, it'll disturb the Oort cloud and send a whole load of comets in our direction, and we can expect to get a lot more impacts. Here, if we look at extinctions that have happened over the last 500 million years or so, we notice that extinctions tend to peak not necessarily every 100 million years, but certainly we get quite a few extinction level events over 500 million years or so. The last one on the right hand side, the KT one, that's the boundary between the Cretaceous and Tertiary era. That's the impact 60 odd million years ago that killed the dinosaurs and of course allowed us to evolve into the creatures that we are. So it looks like extinction level events occur on these sorts of timescales. And although this is an artist's impression, we can expect large chunks of rock to come our way on a timescale of 10 to the 8 years into the future. This particular chunk of rock, if you look to the left, seems to be heading for Italy. Yep, okay, bad news for Italy, but probably bad news for the entire Earth. If the rock is big enough, it could result in an extinction level event. Almost certainly it would result in some species being exterminated. The real question is, will that include us? We've got a little bit of time to figure out, if a rock does come our way, what we're going to do about it. So maybe with the right amount of planning, that won't be such a problem. The second consequence of having a lot of stellar neighbours is that one of them might go supernova. At the moment, we haven't got any stellar neighbours which are massive enough to be supernova candidates. But if we have a lot more neighbours when we are inside a spiral arm of the Milky Way, maybe one of them will be a supernova candidate. If a supernova went off within 100 light years of Earth, it's been calculated that could well be a danger to Earth. Remember, Betelgeuse at 600 light years is considered relatively safe. 100 light years distance, that would be a problem. And if there was a supernova less than 20 light years distant, it could conceivably produce enough radiation to end all life on Earth. And if that sounds a little bit alarmist, bear in mind that there is evidence that there have been supernova relatively local in the past. Supernova within 100 light years have left deposits of a particular isotope called iron-60 in Earth's sediments. Iron-60 is a radioactive isotope which is made by supernova but is not naturally occurring. Iron-60 will decay over millions of years into other elements. It'll decay into cobalt and then into nickel. Which means if we see iron-60 in the Earth's sediments, which we do, that indicates that it's got there because of a supernova. It's not a naturally occurring isotope, and therefore it hasn't been around for billions of years since the Earth was formed. It's arrived relatively recently because we know that the radioactive decay of this isotope would mean that if the supernova was, for instance, 1 billion years ago, well, the iron would have decayed away to cobalt or nickel. So it looks like we have had supernova go off in the distant past. If it's happened before, it can happen again. Still on a timescale of 10 to the 8 years. The fact that the moon has been robbing the Earth of angular momentum and slowing the Earth down, that's been continuing now for tens of millions of years. So effectively the moon raises tides on the Earth, and that tidal interaction slows the Earth, and the angular momentum is transferred from the Earth to the moon. And as a result, the size of the moon's orbit will increase. The Earth has slowed down to the point where it no longer spins once in 24 hours, it's now once in 25 hours. So the idea of adding leap seconds to keep our clocks synchronized with the rotation of the Earth would have to give up that idea completely. Maybe this would be a good point to decimalize the clocks rather than having multiples of 12 or 6 or 24. But there is a consequence for the moon moving away from the Earth. At some point, the distance from the Earth to the moon will be so large that the disk of the moon will no longer be able to cover the disk of the sun. In other words, we will no longer be able to witness a total eclipse of the sun from the Earth's surface. It'll still be possible to have partial eclipses. It'll still be possible to have annular eclipses where the moon's disk doesn't cover the full sun and we might get a ring of fire around the outside, but no more total eclipses. Perhaps more consequential than simply not having the spectacle of an eclipse anymore, the moon stabilizes the tilt of the Earth, the so-called obliquity. At the moment, the Earth's tilt is at about 23.5 degrees, and it hasn't changed by more than about a degree either side of that, according to historical records. But once the moon is further away from the Earth, perhaps when it's more than 25% further than it is now, it is possible that the tilt of the Earth is no longer coupled to the angular momentum of the moon, and it's possible the tilt of the Earth could change. So the stable seasons that we've had for quite a while now could suddenly change if the tilt of the Earth changes. There could be wild variations in the Earth's climate from this point onwards. Still a timescale of 10 to the 9 years into the future. The Voyager gold disc, shown on the right-hand side, which is a phonograph to be played by a stylus as the disc rotates. It's thought that this disc should last for 1 billion years based on how quickly it evaporates. Why do we think this is going to last longer than, for instance, the plaque on the front of on the side of the Pioneer spacecraft? Well, it's simply because the gold disc on the Voyager spacecraft are protected by a cover, as shown on the left-hand side. And so that is going to get rather pitted and eroded, but hopefully the disc itself should survive for maybe 1 billion years into the future. One downside is that although the disc is protected by the cover, it's the cover on the left-hand side which contains the instructions for how to play the phonograph. So if Voyager travels through various solar systems and doesn't get picked up for the first 1 billion years of its travels, well, anybody that then captures the spacecraft and tries to read the disc, they'll have to figure out how to play the phonograph without the benefit of the instructions as to how to place the stylus in the groove and the speed at which the record should be played to give you a true renditions of the greetings from Earth that are recorded on the phonograph. But maybe if the species is intelligent enough to actually pick up the Voyager spacecraft, maybe they can figure out how to play a long playing record without any instructions from us. 10 to the 9 years into the future, we're still talking about a few billion years hence, the sun is going to change. It's not quite ready to be a red giant, but it is changing. The sun's luminosity will slowly increase as it heads towards the red giant phase. It's been calculated that its luminosity would increase perhaps by 10% for every billion years. And that's going to drive the surface temperature of the Earth up to something of order 80 Celsius. A little bit warm for most people. Going underground isn't going to help. I think we'd have to leave the Earth and then come back when it's cooled off a little bit. But we know the sun is going to swell up into a red giant after quite a few billion years, and the surface of the sun is going to increase, expand until the surface of the sun is something like where the current orbit of the Earth is. So you think to yourself, well, if the surface of the sun is heading in our direction, well, is that going to be a problem for little old Earth? Some people say the Earth will be engulfed by the sun, and that might be true, but it's not necessarily the case. Yes, the sun is going to increase as a red giant until it's about the size of the Earth's orbit. But as the sun expands, there will be strong solar winds resulting in the sun losing quite a bit of mass. So if the sun is less massive, there's less gravity pulling on the sun, which means the size of the Earth's orbit is going to expand. So this little cartoon on the left shows what might happen. As the sun gets bigger, the Earth is going to get further from the sun. So yes, the sun will engulf the Earth's orbit, or at least the orbit of where the Earth used to be. But the Earth will probably be in a new orbit, perhaps out somewhere where Mars is now. So it's not necessarily going to get engulfed by the expanding sun. The Earth might survive. Let's assume it does for the time being. Once the sun has gone through its red giant phase, it's going to slough off its outer layers and produce a planetary nebula, and the core of the sun, the star that's left, is a white dwarf. So this will be on a timescale of many billion years, heading towards 10 billion years into the future. But if the Earth survives the red giant phase, it has another problem to contend with, and that is the core of the Earth is going to cool, and the Earth will lose its magnetic field. The cooling of the core is nothing to do with what the sun is actually doing, the red giant phase, the white dwarf, etc. The core of the Earth is being kept molten at the moment by radioactive decay of elements that are in the Earth's core. And these elements are decaying, releasing radioactive particles. That heat is keeping the core molten, and a rotating molten core is a dynamo that generates the Earth's magnetic field. Eventually, the radiation of the elements in the Earth's core will not be enough to keep the core molten, and the core will freeze and we'll lose our magnetic field and be exposed to radiation from the sun, perhaps not so important, now it's a white dwarf, but we'll also be exposed to cosmic rays. It's thought that maybe this is what happened to Mars some time ago. Mars is rather smaller, its core would have cooled off faster, and maybe its core froze a long time ago and hence it lost its magnetic field and ultimately lost its atmosphere. So perhaps we're going to survive the sun going through a red giant. Perhaps we'll survive the Earth losing its magnetic field. They say that bad luck comes in threes. At about the same time, we are going to have a collision with the Andromeda galaxy. In other words, on a timescale of a few billion, heading up to 10 billion years, the Andromeda galaxy is going to come crashing our way. So for those of you who like astrophotography, photographing the Andromeda galaxy, in a little while you won't need a telephoto lens anymore. You'll need a wide-angle lens as it gets closer and closer. As the two galaxies pass through each other, there's going to be a riot of new star formation. It's unlikely any stars will collide with each other. The sun is unlikely to hit anything in the Andromeda Galaxy. It's possible that tidal effects could pull the sun out of the Milky Way. If that happens, the planets will simply go with it. So it's not going to be disastrous for the solar system. Eventually, the two galaxies will pass through each other and then eventually settle down in a little dance in which all of the stars will eventually orbit one mega galaxy, and the two black holes, one originally the black hole of the Andromeda Galaxy and the other the black hole at the centre of our Milky Way, they will orbit each other for a while and then eventually they will coalesce and merge together into one supermassive black hole. That will be on a timescale of beyond 5 billion years into the future. On a scale of 10 to the 11 years into the future, the slow dance between the moon and the Earth will eventually come to an end. In other words, they will end up getting locked together. One day will equal 1 month. The length of time it takes the Earth to spin once on its axis will be the same as the length of time it takes the moon to go round the Earth. So they will be locked in sync. The Earth will be tidally locked to the moon. One side of the Earth always facing the moon, just as what's been happening with the moon for billions of years, where one face of the moon has always been facing the Earth. So it means that from certain places on the Earth, the moon will always be in the sky, it'll never rise and it'll never set. And there will be half of the Earth which will never see the moon. It'll simply be never above their horizon. And this particular picture, by the way, it looks a bit odd, but it is a genuine picture of the full Earth and the full moon, but taken from some distance away, so we're seeing the far side of the moon, not the more familiar near side of the moon. That's why it looks a little bit odd. On a timescale of 1 trillion years into the future, 10 to the 12 years into the future. Here's what's going on in our local group, our local batch of galaxies. There's Milky Way in the centre, surrounded by quite a few small satellite galaxies, dozens if not 100 or so small satellite galaxies. Now, we know that M31, the Andromeda Galaxy, is going to merge with the Milky Way, but ultimately the same will occur for the M33 Triangulum Galaxy. And all of the satellite galaxies, essentially everything in the local group, will eventually merge into one mega galaxy. It's unlikely to be a spiral galaxy, as indicated by this little icon, probably more likely one large elliptical galaxy. So in 1 trillion years, all of the local group will be one galaxy. But what's happening to the other galaxies beyond the local group? Well, a few years ago, I gave you a short talk called Ancient Light, in which I described how it's possible now to image galaxies, even galaxies that are receding from us at twice the speed of light. This is something I did as a lockdown challenge during the COVID pandemic. So at the moment, it's possible to see galaxies at enormous distances, even if they have huge recession velocities. And indeed, when you look at a Hubble picture, such as the one on the right-hand side, quite a significant number of those galaxies are distant enough from us that their recession velocities are greater than the speed of light. Some of them will be relatively close to us, but most of these galaxies are very distant. But on a timescale of 10 to the 12 years, we know how the universe at the moment is expanding, and if we could assume that it continues to expand, at the moment it looks like the expansion is accelerating. Even if it were only to accelerate by a modest amount, we can calculate that on a timescale of 10 to the 12 years into the future, the expansion of the universe will be such that it will have taken all galaxies beyond our ability to see them. And it's sobering to realise that if a civilization comes along in 10 to the 12 years' time and builds themselves a telescope to look out into the universe and say, I wonder what's out there, what will they see of the universe? Well, the answer is they will see essentially nothing outside of their own galaxy. So they might still occasionally see a few stars in their own galaxy if they were to do the equivalent of a Hubble Deep Field. It doesn't matter how good their telescope is, it doesn't matter how good their cameras are, At some point, it will simply be impossible to pick up the light from distant galaxies. In other words, galaxies other than the ones in which you are currently residing. So in that sense, we live in a rather privileged time where it is possible to see billions, if not trillions, of galaxies in the observable universe. That will not always be the case. I said in the beginning of everything that it took 3 minutes to make all the hydrogen in the universe. But after trillions of years, it's starting to run out. And if there's no more hydrogen, that means no more star formation. Now, some people disagree. Just a little aside, some scientists say, well, maybe that's not true. Maybe you don't need hydrogen to make stars. Maybe you can make stars out of something else, heavier gases. Might it be possible to use gas with a heavier proportion, with a greater proportion of heavy elements to make stars, even if you've got no hydrogen? It's been calculated by some that it might be possible to generate a star in which there are fusion reactions in the core, but the surface temperature turns out to be quite low, even lower than a red giant with a surface temperature of 3000 Kelvin. Maybe it's possible to make stars with surface temperatures of hundreds of Kelvin. Might it be possible to make a star with nuclear reactions at the core, but ice in the atmosphere? Frozen stars. And no, I'm not talking about the Disney version of Frozen, so that picture on the left, if that's the sort of picture you've got in your head, then let it go, because we're talking about frozen stars in which there might conceivably be ice in the surface, even though there are fusion reactions in the core. Some scientists say that might be possible. Others say, no, sorry, you absolutely need hydrogen to make stars. The first process of making a star needs the lightest of gases. So to work out the consequences, we just have to think for a second about what the universe as a whole is doing. We're going to go a little further into the future, but we need first to think, what is the universe doing? So here's an indication of what we think the universe is doing: the expansion of the universe, the size on the vertical axis and time on the horizontal axis. So you can see we've got now indicated where the relative size of the universe is 1. And notice that the 4 coloured lines correspond to how much stuff there is in the universe, how much matter, how much energy in the universe. And we don't, strictly speaking, know which coloured line we're on. And depending on which coloured line we're on, that dictates not only how the universe is going to behave, but also what it's done in the past. In other words, how long is it since the Big Bang? If we are in a universe in which there's a very large amount of matter, then we're on the orange line. And that means there's so much matter in the universe, gravity will stop the expansion, and the expansion will reverse, and we'll end up with a big crunch many billions of years into the future, a so-called closed universe. But all our observations would indicate that we're not in the orange universe. There's not that much mass out there. When I was a lad, it used to be thought that probably we're on the green line. In other words, the total amount of mass and energy is such that we will follow the green line. The universe will expand and it won't come back to a big crunch. But recent observations have told us that we think we're actually on the red line. The amount of matter and energy in the universe means that the expansion of the universe will continue indefinitely. Not only does the red line continue to go up, notice that its gradient is increasing as well. Not only is the universe expanding, the rate of expansion is continuing to increase as well. So things might change in the future, but at the moment all indications are that we're on the red line and the universe will continue to expand forever. So coming back to the consequences of, okay, so what does that mean for the future? I've had to change that timeline along the top in order to make any progress whatsoever. We're going to change gear because each small box at the top now represents 1,000,000 times further into the future than the previous box. So we're now talking about 10 to the 12, 10 to the 18, 10 to the 24, 10 to the 30, 10 to the, I don't know, is this a zillion years, a gazillion years? We're running out of adjectives to describe these times. We're just going to have to rely on the fact that we're talking about 10 to the relatively big numbers of years into the future. So we said, before I took this little diversion into what the universe is doing, we said that it took 3 minutes to make all of the hydrogen, but the hydrogen is now running out. Now, some stars live for an awfully long time. Our sun might only live for 10 billion years. Relatively low mass stars could live for trillions of years, or tens of trillions, who knows, maybe hundreds of trillions of years. But no star lives forever. So if the hydrogen is running out and we can't make new stars, what does that mean? There will come a time when there are no more stars shining. The age of starlight will come to an end. The stars will continue orbiting their galaxies for a while. There will be dead husks drifting through space like zombies. White dwarfs, neutron stars, black holes. It might seem odd to talk about a white dwarf not shining, but with no nuclear reactions to keep them hot, white dwarfs will simply cool down. Remember, these are the cores of stars that have come to the end of their lives. So yes, they start their lives fairly hot, but it won't be long before they cool down to the point where they are simply black dwarfs. So no stars are using nuclear reactions to keep them shining anymore. Some stars will be ejected from the galaxy. Some stars will be eaten by the supermassive black holes that occur at the centre of all galaxies. Magnetic fields have been mapped out in some galaxies. It's a bit difficult within our own galaxy, but magnetic fields in other galaxies have been mapped out, for instance, by SOFIA, the Stratospheric Observatory for Infrared Astronomy, a telescope in the back end of a 747. That's mapped out magnetic field lines, and we believe that these field lines are responsible for funneling matter into the supermassive black hole at the centres of galaxies, and that will keep the supermassive black holes fed on anything that's left after the stars have stopped shining. We can ask what's going to happen to all of the atoms. We know that atoms have positively charged protons in the nucleus and negatively charged electrons buzzing around them. And it's thought that maybe protons will decay and change into something else. And if they do, that means every atom in the universe will fall apart. Now, we don't know the timescale on which this is going to happen. Particle physicists say it's unlikely to happen on timescales less than this. In other words, it's not going to happen in the next 10 to the 36 years or so, but it might happen at that point or sometime after that point. But even if we assume that that doesn't occur and that protons don't decay, well, still atoms will not last much longer, because the only atoms in the universe are in black dwarfs, and eventually those black dwarfs will evaporate into radiation. That's a quantum mechanical effect I'm not going to go into details about. There are no atoms in neutron stars, there are no atoms in black holes, and eventually there'll be no atoms because black dwarfs will evaporate. There will be black hole mergers because galaxies in clusters will end up merging with each other, just as I described with Andromeda colliding with the Milky Way, and the black holes at the centre of those two galaxies are going to merge. The same will be true of galaxies in larger clusters, clusters of thousands, if not tens of thousands of galaxies. So the supermassive black holes can, in principle, grow to not just millions or billions of solar masses, they could grow until they are trillions of solar masses. But even black holes are not eternal. We think they will evaporate, providing that you wait for a really, really, really long time. So let's ask the question, why do black holes evaporate? Well, quantum mechanics tells us about particles and antiparticles, and we can make matter and antimatter by borrowing energy, make matter and antimatter as long as they annihilate and pay back the loan of the borrowed energy on short timescales. In other words, we can borrow energy from nothing, make matter and antimatter, they then annihilate, and bam, they pay the loan back again. We think that's happening all the time. Quantum theory is based on the fact that this is happening all the time, and basically we just don't notice. How does that help us understand what's going on with black holes? Well, Hawking and others said, well, if this is going on all the time, what happens if this process happens just outside an event horizon? So let's imagine that's the event horizon of a black hole. What if we borrow some energy, make some matter and antimatter, and one of them falls into the black hole and the other one doesn't? Now they can't annihilate. It looks like something has been radiated from the black hole. It looks like there is something leaving the black hole. It is losing energy. That's now become known as Hawking radiation. It's a conjecture. We can't prove it because we can't see this radiation. It's not strong enough for us to measure directly. But essentially all scientists believe that this is probably happening according to our understanding of quantum theory and particle physics. The radiation from a black hole increases with decreasing mass. So as the black hole evaporates and gets smaller and smaller, the radiation goes up and up and up. Finally, it disappears in a flash of radiation. So large black holes will start radiating only very slowly. As they get smaller and smaller, they'll radiate faster and faster and faster. Even the supermassive black holes that we've been describing at the centers of galaxies, even the ones that might grow until they are trillions of solar masses, even they will evaporate eventually, though it will take many trillions of times longer than for stellar mass black holes. In other words, it's difficult to imagine, but the calculations tell us this will happen. So, have we actually reached the end of time? Well, we've reached the end of that timeline, and we can ask ourselves what's going to happen on a timescale of, let's say, 10 to the power 100, which is a Google. Not that Google, that's simply a misspelling of the mathematical Google. What's going to happen on a timescale of 10 to the power 100 years? It's been calculated that after a Google years, the last black hole will have evaporated. And that means there will be no matter left anywhere in the universe. So after this point, nothing happens. So time, you could say, becomes meaningless. The universe will continue to expand. There will be radiation, but there will be no matter. Just to show you what a Google actually means in zeros, we don't normally write it out in full, but there it is. 10,000, million, you can do it yourself. There's an awful lot of zeros there. Impossible to imagine how big that number is, but just because it's something that we can't imagine or visualize doesn't mean we can't do the calculations. Doesn't mean we can't calculate how fast this black hole evaporates, how long will it take if it's really massive. And we think 10 to the 100 is the length of time it'll take before the universe gets thoroughly boring, because from this point on, nothing happens. Eternity is a very long time, especially towards the end, as Woody Allen said some time ago. Another way of thinking of these ridiculously long numbers is to try and put it in some sort of human perspective, which is what the cartoon XKCD has been doing for many years. They once said that a human is simply a system for converting dust billions of years ago into dust billions of years from now via a roundabout process which involves checking email a lot. That's an interesting perspective on the human condition. But let me finish on a slightly more upbeat note rather than simply end by saying the universe is going to get really, really boring. You could say we live in a golden age because the sun is middle-aged and stable and well-behaved. And the moon is at just the right distance to stabilise the Earth's axis and hence stabilise the Earth's seasons. And as a bonus, it also gives us the spectacle of a total eclipse of the sun every once in a while. And thanks to evolution, we are able to explore and discover and understand the universe in which we live. And we can do that by building spacecraft and sending them out to have a closer look at some of our nearest neighbours. And we're also able to build telescopes to look out into the universe and see billions of galaxies at distances of billions of light years. We could not have done this in the very early universe because we needed generation upon generation of stars to make all the heavy elements for us. We needed stars to convert hydrogen into helium, to convert helium into carbon and nitrogen and oxygen and calcium and phosphorus and iron, and all the elements that we need to make us. And as we've just seen, trillions of years from now, the universe is going to be very dark and very boring. So you could say the best time to exist is now. Thank you.